Hello everyone, this is Alfia Tansal, lecturer in physics, faculty of Arihant College of Arts, Commerce and Science. Talking about electromagnetic induction, we have lately seen what is self-inductance. In today's lecture, we'll be seeing what is mutual induction. Talking about mutual inductance between two coils is defined as the property of the coil due to which it opposes the change of current in the other coil, or you can say in the neighboring coil. When the current in the neighboring coil changes, the flux sets up in the coil, and because of this, the changing EF flux EMF is induced in the coil is called mutually induced EMF, and the phenomena is known as mutual inductance. Two coils, say A and B, are placed nearer to each other. When the switch S is closed and the current flows in the coil, it sets up the flux phi in the coil. An EMF is induced in the coil, and if the value of the coil, its current is changed by changing the value of the resistance R, the flux linking with the coil B also changes. Because of this change in current, this phenomena of linking flux of the coil A with the other coil B is called mutual inductance. Now, if we have to derive what is mutual inductance, here we are going to consider a case of two coils placed side by side. Suppose a fixed current I1 is flowing through the coil 1. Due to this current, a magnetic field B1 will be produced in the nearby region surrounding the coil 1. The magnetic flux phi 21 linked with the surface S2 of the coil 2 due to magnetic field B1 is given as phi 21 is equals to integration of S2 B1 into del A. If the position of the coils in the fixed space, then phi 21 is directly proportional to I1. The induced EMF in the coil 2 is given by E21 is equals to minus d phi 21 upon dt, that is equals to minus M21 into di by dt. Now, when the current I2 flows through the coil 2, magnetic flux linked with the coil 1 is given by phi of 12 directly proportional to 2, that is the equation number 3. Phi of 12 is equals to M12 into I2, that is equation number 4. M12 is equals to phi 12 upon I2, where M12 is the mutual inductance of the coil 1 with respect to the coil 2. The induced EMF in the coil 1 will be E12 equals to minus M12 into di by dt. By symmetry, we have M12 equals to M21 equals to M. Now, if you have to define mutual induction, the mutual inductance of two circuits is equal to the magnetic flux link with one circuit per unit current in the other circuit. The mutual inductance M of two circuits in the magnetic flux link with the secondary circuit per unit current of primary circuit. Mutual inductance is defined as the value of induced EMF produced in the secondary circuit per unit rate of change in the current in the primary circuit. The unit F of mutual inductance is Henry capital H equals to volt upon ampere seconds is equals to ohm into seconds. Explain coefficient of coupling between two circuits. Now, what is coefficient of coupling? The coefficient of coupling K is a measure of the portion of the flux that reaches the coil which is in the vicinity of the coil 1. Now, greater the coefficient of coupling, greater will be the mutual inductance. Inductance of any circuit is proportional to induced voltage it can develop. This is equally true for mutual inductance, M being directly proportional to E21, equation 1, where E21 is induced EMF developed in the coil 2 due to the portion of the flux from the coil 1 reaching the coil 2. We have induced EMF E21 equals to K into phi 1, that is the equation number 2. But induced EMF is also proportional to the number of turns in the coil. E21 is directly proportional to N21 into K phi 1, termed as equation number 3. E21 is directly proportional to N2 into K into N1, that is equation number 4. Also, L is directly proportional to N square, or N is directly proportional to under root of L. N1 into N2 is directly proportional to under root of L1 into L2, that is nothing but under root of L1 into L2, termed as equation 5. Now, if we substitute equation 5 in replacing E21 with M in equation 4, we have M equals to K under root of L1 L2, that is equation number 6, where K is nothing but the coefficient of coupling, which is usually less than 1 unity. If we consider K to be equal to 1, then the two coils will be perfectly coupled and M will be equal to under root of L1 into L2. If we say K is greater than 0.5, the two coils are tightly coupled. If K is less than 0.5, the two coils are loosely coupled. If L1 equals to L2, then a coil with self-inductance L is coupled to itself with mutual inductance M equals to under root of L1 into L2 equals to under root of L square equals to L. Now, large values of mutual inductance are not always desirable because a large value of mutual inductance is desirable for a transformer, but higher mutual inductance is not desirable for home appliances such as electrical clothes dryer. A dangerous EMF can be induced on a metallic case of the dryer if the mutual inductance between its heating coil and the case is large. In order to minimize its value, the heating coils are counterwound so that their magnetic fields cancels one another and reduces the mutual inductance with the case of the dryer. Factors on which coefficient of coupling depends. Now, if the coils are wounded on a common iron core, the coefficient of coupling can be considered as unity. For two air core coils or two coils on separate iron cores, the coefficient of coupling depends on the distance between the two state the factors on which coefficient. When the coils are kept parallel, the coefficient K is maximum. If the axes of the coils are at right angles, then we say that K is minimum. In order to prevent interaction between the coils, the two coils should be oriented at right angles to each other. If two coils are wound on a common iron core, the coefficient of coupling is considered to be unity. For two air core coils or two coils on a separate iron cores, the coefficient of coupling depends on the distance between the two coils and the angle between the axes of the two coils. Now, what is a transformer? A transformer is a device used in power transmission of electrical energy. The transmission current is AC. It is commonly used to increase or decrease the supply voltage without a change in the frequency of AC between the circuits. The transformer works on a basic principle of electromagnetic induction and mutual induction. The principle on which it works is based on the principle of mutual induction, that is, whenever the magnetic flux linked with a coil changes, An EMF is induced in the neighboring coil. Construction. A transformer consists of two sets of coils, primary and secondary, insulated from each other. The coil P is called the input coil and the coil S is called as the output coil. The two coils are wound separately on an inlaminated soft iron cord. Working. When an alternating voltage is applied to the primary coil, the current through the coil goes on changing. Hence, the magnetic flux through the core also changes. As this changing magnetic flux is linked with both the coils, an EMF is induced in each coil. The amount of magnetic flux linked with the coil depends upon the number of turns of the coil. Let phi be the magnetic flux that is linked per turn with both the coils at a certain instant t. Let Np and Ns be the number of turns of primary and secondary coils. Np phi is equals to magnetic flux linked with the primary coil at a certain instant t. Ns phi is equals to magnetic flux linked with the secondary coil at a certain instant t. Induced EMF produced in the primary and the secondary coil is given by Ep is equals to minus d phi p upon dt, that is equals to minus Np into d phi by dt, termed as our equation number 1. Es is equals to minus d phi s upon dt equals to minus s into d phi by dt, termed as our equation number 2. Dividing equation 2 by 1, we get Es upon Ep is equals to Ns upon Np. Equation 3 represents the equation of the transformer. The ratio Ns upon Np is called turns ratio. Now, for an ideal transformer, the input power is equals to the output power. Ep into Ip is equals to Es into Is. Es upon Ep equals to Ip upon Is. From equation number 3 and 4, we get Es upon Ep equals to Ns upon Np equals to Ip upon Is. Case 1, when we say that Ns is less than Np, then Es is less than Ep, that is a step-up transformer, and If is less than Is. Current in the primary coil is more than that in the secondary coil. Case 2, when Ns is less than Np, then Es is less than Ep, that is the step-down transformer, and Ip is less than Is. Current in the primary coil is less than that in the secondary coil.